Gurgy!
Oh, hello YouTube. I did not see you over there. How's everyone doing?
Gurgs!
What?
You won't be able to hear them back. You do know that, right?
Ah, shit.
Now let's get started. We examined whether it would be quicker to go up or down the elevator, or just take the stairs. Our null hypothesis is that there was no difference in times between taking the elevator versus the stairs.
Our alternative hypothesis is that the stairs would take a shorter time than the elevators. After hours of experimentation, Billy and I finally have the results of our test. Let's walk you through it. To ensure the accuracy and the validity of our test, we used the Alpha Phantoms method. This acronym is defined right over here.
So, with Alpha Phantoms, we have A, which is for alpha level. We will go over that shortly. Parameters. We used an N value of 15. That means we used 15 trips up and down the stairs and 15 times going up and down the elevator total. Hypotheses, we already went over that. Assumptions and conditions, we will go over that in a minute. Name of test, the conditions will determine which test we use. Test entry into the calculator, that's the T. Then we obtain our p-value. P is the probability that the null is true. That is why if we get a low p-value, we reject the null. Therefore, with that p-value, we use that to make our conclusion. So, in context, this is where the exact wording of the null comes in. Whether we reject it or not tells us about the real world as a whole.
It may sound complicated, but it's a lot simpler than Gurgs here made it sound.
Billy, are you trying to make me sound like a...
So back to the start, we had to define an alpha level.
This does not involve a medical procedure or anything of the sort, so lives are not at stake with the results of this test. Therefore, an alpha level of 0.01 would be rather overzealous.
However, this is a common scenario, stairs versus elevator, so we figured an alpha level of 0.1 might be insufficient.
The only common alpha level remaining is 0.05. Assumptions and conditions. For our test, we had to make sure that all appropriate assumptions and conditions for this test were met. Now, I do feel obligated to warn you all that in order to make the video meet the time constraint of 10 minutes, we had to speed this next part up to double speed. So don't be shocked, if you don't mind a bad pun, that we sound like bloody chipmunks. Carry on.
So here we will go over them with our checklist for conditions sheet. Since we are looking at a time, a continuous variable, we are looking at means. We have two means here, stairs and elevator, so we have two samples to analyze. Stair times and elevator times are random. The starting position of the person and elevator is randomly assigned. Stair times and elevator times are independent of the next, as well as the mean of both times not impacting the next. Here we have the box and whisker plots for the stairs. As you can see, all three look rather decently normal, especially the overall. However, the person initial down is skewed extremely heavily to the left, and the person initial up is skewed, although not as heavily, to the right. What this means is that there are a lot of slower times going down the stairs, where I start up, and a lot of times lower than the mean going up the stairs, where I start down. However, all three means are close to 15.6. Here we have the box and whisker plots for the elevator when it starts at the same position as the person up or down the stairs. For the up graph, we have, actually for both up and down, we have an extremely narrow spread, and for the initially up where we go down, you can see that it takes a really long time, and for initially down, it's relatively shorter by comparison. However, overall it's a very wide spread, and you can clearly see it's bimodal, so we did split that up when doing our histograms. Here we have the box and whisker plot for when the elevator does not start at the same floor as the person. As you can see, for the 1-0, which by the way is when the elevator starts up and the person starts down, we have a spread of about 1.1 seconds, since the times range from 42.6 to 43.7. For 0-1, which as I'm sure you can figure out is when the person starts on top and the elevator starts on bottom, we have a spread of about 2.8 seconds, from 40.4 to 43.2. Overall, this is a fairly normal spread. Here we are with our stairs histogram. The stairs histogram is nearly normal and unimodal with a slight gap below the mean. The is our histogram for the elevator and person starting at different floors. This is nearly normal, unimodal, and symmetric. The spread is from 40.43 to 47.43 seconds. The center is at 43.23 seconds. There's a slight gap just above the mean. Here's our histogram for when the elevator and person start at the same floor. This histogram appears to be bimodal once again. We will have to proceed with extreme caution from this point on. Here's our histogram for when both the elevator and the person start down. This graph is bimodal and symmetric. The center is at around 15.4 and the spread is from 14.94 to 15.85 seconds. There are two gaps in this graph. This is our histogram for when both the elevator and the person start on top. This histogram is strongly skewed to the left. It is unimodal and the spread is from 19.34 seconds to 19.7 seconds. The center is at about 19.5 seconds. The only other condition is that we must use the elevator and the stairs each less than 10% the number of times it's been used of all time, and 15 is less than 10% of the number of times the stairs have been used or the elevator has been ridden. Since we have met all of these conditions, we can now use a two-sample t-test using our calculator. Now that we have named the test we are going to use, the two-sample t-test, we must actually execute said test. To do this, we entered all the stair times into list 1 in our calculator, all the elevator times into list 2 in our calculator, and then selected two-sample t-test for our test. We set list 1 as L1, list 2 as L2, frequency as 1 as both, that's how it was initially, and we just never mess with that, so just don't mess with that at all. And then for our alternative, we said mu1 is less than mu2, since we want as our alternative the stairs to be less time, meaning that they're faster. And no, we did not pool our data, the means and standard deviations just aren't even close together. Then we calculate.
Our p-value is astonishing low, 0.004, much less than our alpha level of 0.05. So we reject the living null hypothesis. Therefore, we have evidence that there is a difference in how long it takes to go up the stairs versus the elevator. Now we shall construct ourselves a 95% confidence interval. Since our interval is entirely negative, we know that the time for stairs is definitely less than the time for elevator.
Do know that we only went up and down one floor, and not all the elevators are the same. Also, Gurgs did happen to go diagonally up the stairs, across, and more directly down the stairs.
$15.05.
However, this is not too significant and likely did not greatly affect the result of our test, especially considering the variances of the elevator times.
Well, anyways, that concludes our video. Now enjoy some jolly good bloopers that we threw in at the end of our vid.
How's everyone doing? What?
Oh!
We examined a cut.
Overall, it is a somewhat widespread of about 3-ish seconds. That's not a widespread. What am I talking about?
Now let's get started. We examined whether it would be what?
Over here, we have the Yes, that's a histogram. Oh, blast. So we reject the living trash out of our null hypothesis.
Now let's get started. We examined whether it would be quicker to go up or down the elevator, or just take the stairs. Well, to ensure the accuracy of and validity, what does that say?
Isn't that mine? That's...
Okay, wait. That's fine.